Sorry. Chase has been my guy for a while. Is it on? I can't even tell. Is there any picture yet?
22%. It's a little
Ooh, this thing has all four. It says it's only 22%. Yes. I didn't want to record all that stuff because it just wasn't that necessary. This is a little crooked, so at times I may appear.
Yeah.
I may appear a little bit off. Okay, are we ready?
Yep.
This one we will not be stopping. This class, unfortunately, you don't get a break. You only get a break in the 2.5-hour classes. All right, is it how we start?
It's on.
We are in, okay, so that's 30 seconds of wasted time. We're going to do two major topics today. The first one is work. Now, this is a physics application, and that just scares people right off the bat. But the thing is, if you're doing calculus without application, there's a problem, because you're saying, I'm doing all of this stuff, but I don't know when or how I would ever use it. Work is like the lowest level. Now, if you're taking physics, this is one of the things that people don't dwell on in math. In physics, units are just as important as numerical answers. Now think about all the math classes you've ever had. You know, it could be algebra. You're doing graphing stuff. You're doing, maybe distance, rate, time problems, in baby algebra. But a lot of times you don't have units in your answers. You don't even worry about it. In calculus last semester, when you were doing integration problems, you did volumes by rotation. You did surface areas. You did arc lengths. Did you give units to any of those answers? Think about it. No. Shouldn't they all have units? Because I'm measuring a length or an area or a volume? Yes. But in the math class, we're way more focused on the correct mathematical procedures and the correct numerical answers. But it's a bit artificial because in reality, everything has units. Every graph you've ever done, even in a remedial algebra class, the x and y axis actually have to have units for it to mean something. So when you're asking for the slope of the line, that slope has to be a rate. Think about that for a moment. Yeah, we never worried about that. Now you have to start worrying about it a little bit, and in this class. And so this is the part of the class where we do a little bit of a crossover, specifically so we can give answers that have units. So when it comes to work, what are the units? Ooh. Well, let's back up a little bit. Force. What is force in the simplest sense? It's a product of two things. Anybody know what it is?
Oh, mass times acceleration.
Beautiful. Mass times acceleration. That's what force is. It's mass times acceleration. Now, I'm going to stay away from vectors, okay? This is all vector related, but we don't do the vector part of this until Calc 3. So right now you're a little bit off the hook. It's a little bit artificial, but I'll explain why we do it that way, because we want to get the numbers right. Later we'll add. So if it's mass times acceleration, well, what is mass? Mass is an interesting concept. If you look up mass, the best description I ever saw of mass when I looked it up, mass is how much stuff something is made of. Isn't that a great definition? How much stuff? So if within your body you were mostly just, I don't know, styrofoam, you wouldn't have a lot of mass. But within your body, if you were mostly, cement, you would have a lot of mass because your density would be different. So mass is how much stuff something is. It has nothing to do with weight whatsoever. How many here grew up outside of the United States? You grew up in a metric environment, which makes me always laugh because I have fun with this. So when I ask you how much you weigh, you're going to give me an answer in kilograms. You might as well give me your age or your height because it has the same meaning mathematically. You do not weigh any amount of kilograms. That makes no sense. Kilograms is mass. And I have never heard a human being in my entire life tell me how many newtons they weigh, because that would be the correct answer, by the way, is how many newtons do you weigh? Because if you're going to use metric, you can't give me mass. Mass does not refer to weight, unless you're applying it to what? What acceleration would we apply to it? Gravity. And so therefore, would you weigh the same on all parts of planet Earth? No. The top of Everest, you're going to weigh a little bit less. What if you're on the moon? Weigh a lot less, about 1/6 as much. What if you're on Jupiter? Weigh a lot. Yeah, your weight is dependent on the gravity, but your mass never changes. So if you're going to get it right, don't do it. Now, I was a competitive athlete most of my life. You know, and I trained people for years and years and years. I was a competitive power lifter a million years ago, and everything is measured in kilograms, which is funny because nobody knows the difference. Because at sea level, a kilogram weighs about 2.2046 pounds. It doesn't weigh that much everywhere, but that's the number they use, which I find it very interesting because there are a lot of competitions at high altitudes. I mean, have the Olympics ever been held at high altitudes? Mexico City, one of the most famous, 1968. That's when Bob Beamon jumped 29 and 2¼ inches when the world record was 27 something. We had the fastest 100 meters ever run. All these world records were set at that Olympics partly because they said the elevation. But the problem is they used sea level mass weights. Nobody weighed that much. They all weighed a little less. He said, well, how much less? When you're over 200 pounds, now it's a measurable less. Now maybe it's a ½ a pound. I mean, it can be important in a weight class situation. So mass times acceleration, that's what force is. What are the units of acceleration?
Mass per meters.
Well, be more loose. Distance per
Second squared.
or time squared. Yeah, probably per second squared. I don't ever see acceleration in anything but seconds. But is it necessarily feet or meters or kilometers or centimeters? It's distance. So usually we say it's displacement per time squared. So this is displacement. Does anybody know what symbol we use for displacement typically in math? It's funny. S. Yeah. What do we use for arc length? Think Calc 1. S. S is always arc length, which is really kind of a strange thing, and it will be the same way through all your math classes. Say, why don't we use something else? Well, what do we use for slope? M. Yeah, that makes just as much sense, right? M for slope, S for arc length. S is sort of the universal displacement. So often we'll write it as displacement per time per time. So what's the first one? Displacement for time. Speed. Good. If we're not talking vectors, we'll often use the term velocity. What is the difference between velocity and speed? How many have ever worked with vectors? Remember, vector is a value in a direction. Speed is the length of the velocity vector, in other words. So if I said I'm going 100 miles an hour, that's my speed. I'm going 100 miles an hour in that direction, that's my velocity. So in a math situation, we kind of treat them interchangeably because right now we're not talking about vectors. So if you said velocity, that's fine. So it's velocity for time, okay? So then how do I get work? Well, work is force multiplied by displacement. So in other words, it's the force multiplied by the distance you applied the force to. So anybody here a weightlifter? Anybody ever work out? Any level weight. So you have the static weight on the bar. It's now moving. There's no force yet. So you decide, I'm going to move that weight. Maybe you're doing a bench press. I'm going to move that weight, however long my arms are, 2 feet. So how much work got done? Take the weight and multiply it by the distance. Because weight and force are the same thing. What is weight? It's the force due to gravity. Oh, so how much you weigh is because of the gravity. So weight and force are exactly the same thing. Weight is a form of force. A lot of folks don't realize that. See, you're in a math class, we never have to think that way. Yeah, but in the physics, you have to know the difference. So when I multiply these, what kind of units do I end up getting? Well, here I'm going to get mass times acceleration, which somebody said velocity. So let's say velocity per time, times displacement. Well, velocity per time, let me go back to displacement per time, and now I'm multiplying that by displacement. Huh. So what does that give me now? Wouldn't that be s squared over t squared? Huh. Well, wouldn't that be the same as the square then of velocity? S per time, mv squared. Have we ever heard that term before? But that's the standard equation, not for work, but for something else. Starts with an E. Energy. Mass times velocity squared is energy. In fact, if I go really, 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 really fast, what's the fastest speed can possibly be, theoretically? Speed of light. What symbol do we use for speed of light? Oh, that's kind of cool. Yeah, that's kind of like the universal speed limit. Okay? That's what that means. MC squared is that, just you're going at light speed rather than something less than light speed. Energy and work are exactly the same thing. It's a context thing. Okay? How much work you got done, how much energy did you use? Same thing. Exactly the same thing. But a lot of folks don't know that, and you go, oh my God, I didn't realize they were the same thing. Now, in English Standard, we use things like foot-pound or pound-foot, which is kind of a weird thing. We don't squish those together into one word. But in metric, if my force is measured in newtons, not in kilograms, if my force is measured in newtons, which is 1 newton is 1 kilogram accelerated at 1 meter per second squared, if my force is in newtons and my displacement is in meters, then what is the unit when I multiply those together? Does anybody know? It starts with a big J. Joules. Joules. That's a good one to know. So if you're in a physics class, it's probably going to be the most common one you use. You're probably not going to do English Standard. You're probably going to do metric. So it's joules. Okay? Now, that's how much work gets done. That's how much energy. Does anybody here ever look at their electric bill? What is the units of measurement on your electric bill?
Kilowatt per hour?
Not per.
Kilowatt hour.
Kilowatt hours. Well, what the heck does that mean? That's energy. Well, why aren't they just saying joules? Why wouldn't they just say
America?
no? That's metric. Well, this is one of my passions. Now, if you go back and look, sometimes I spend time on this in class. I'll spend upwards of 30, 45 minutes. I have something on the basic physics. I wrote a thesis a number of years ago on explosive power training. It's one of the things I've been studying and working with my whole life. I've trained athletes my whole life. I taught martial arts. I just retired last year. I taught for 40 years. I was doing development of things that no one had ever seen before, particularly with the study of weapons, being able to maximize the speed and the power of a hit. The key is power. The key is not force. The key is not energy or work. Power. Power is how fast you're applying the energy. Now, any football fans here? The right answer would be yes. And by the way, I will have a quiz later on your favorite team if you didn't know. I can't believe Max last semester would wear those horrible Broncos jerseys. Anyway, if you watch football, so you're an offensive lineman and you're going to move. I have a lot of force, by the way, and I'm getting a lot of work done as I move you. There's no power involved. That little gnat who's hitting you at 100 miles an hour, he's going really fast, but there's no mass behind him, so there's not a lot of power. Your key in all athletic endeavors would be to maximize your power, because power is force at speed. In other words, how much energy per second are you doing? Now, if I'm in metric, what is a joule per second called? A watt. Kilo just means 1,000. A watt is a joule per second. Oh, so if I did 3,600 of those.
Watt hour.
Well, no, that would be, now if I multiply by time, I get back to energy. If a watt is a joule per time, and I multiply it by time, I get back to joules. That's why it's kilowatt hours, because when you're looking at your light bulb, how long you leave it on is also how much you're paying, isn't it? It isn't just, oh, there's a very powerful light bulb, I just won't turn it on. Well, no, it's how much energy am I using per second. Kilowatt hour means I'm multiplying by 3,600 seconds. The kilowatt means there's also 1,000 of those, 1,000 watts. So that's all what the watt is. So if you're trying to maximize, okay, how many saw the first Austin Powers movie? You guys, do you remember the steamroller? The steamroller got, then they show from the side the steamroller's moving about this fast. And the guy's, like a couple hundred feet away, and he's, freaking out the whole way. It took a while, but eventually the steamroller got to him and squished him. Okay, that steamroller had a lot of force. Not much power. Why? No speed. So the idea of explosive training, which is something I studied, is how do you maximize the amount of power per time? In other words, power, another way of thinking of power, it is force multiplied by velocity, if you go look at the units. So if you are a weightlifter, okay, when I was younger, I did what's called Olympic lifting, clean and jerk and snatch and things like that. You can't do those exercises slowly. I always ask people, why would you ever try to do an athletic movement slowly? Anybody here play basketball ever? Yeah, of course, what happens when you try to jump slowly? Is that possible, to jump slowly? No, it's impossible. You can't jump slowly. You watch football, the running back in the backfield. He takes his time. You're the sprinter on the starting blocks. You take your time. No, you want to be shot out of a cannon. You're trying to reach maximum speed in the absolute shortest duration of time. That's the whole concept. So for athletic endeavors, explosive power is the key thing. Reaching your maximum in the shortest duration of time. Again, like somebody jumping. You're trying to go as fast as you can, not as slow as you can. So anyway, that's the physics behind this. Today we're going to concentrate on work and centers of mass, but the units we're using are important. It's not life and death. It's very simple. So we're going to start with the easiest one of all, and that is the spring problem. Spring, yeah, because this is spring. The spring problem. Now, today I teach differential equations later on today, and they're going to do a spring problem this semester that is much more challenging than the one we're going to do. The problem they're going to do is they're going to have a spring hanging, a weight at the end of the spring, and the spring in some sort of viscous fluid like motor oil or something, and then I'm going to pull on it and it's going to start oscillating, and we're going to have to chart the oscillation and all these things. That's the 255 problem. Nope, our problem, we're going to have a spring going sideways, so there's no gravity, there's no oscillation, and we're going to pull or we're going to compress. Now, there's only a few assumptions we're going to make. First of all, we're going to make an assumption that our spring is long enough that if I stretch it or compress it, I have room to spare. In other words, I'm not going to pull it so far that now it's completely straight and I can't pull any further. Okay? So it's not an infinite spring, but it's a spring that's plenty long enough that I'm not going to run out of room. The second thing we're going to assume, and this is way more important, is that it is of a uniform material. Okay? How many know what a slinky is? Okay. Is a slinky uniform? Yeah, you don't have it a certain thickness and then later it gets really, really, really thick and then gets really thin again. Now, some of you might have like really mean older brothers. What do they do to your slinky?
Twisted it.
Oh, they mess it, they stretch it. Yeah, it's not that slinky. It would be a perfectly engineered slinky. In other words, it's of uniform all the way. It doesn't get thicker. It doesn't have difference. So keep it simple. Okay, so I have a spring. I'm either going to compress it or I'm going to stretch it. And here's one of the cool things mathematically. The amount of force required to compress it will be exactly the same as the force to stretch it. It's not different. I can only compress it so far. I'm not going to go past the point where I can't move. Again, it's a long string, so I'm going to move it in and out. Now, there's something called Hooke's law, which makes this thing so ridiculously simple. It says that every spring, and by the way, we're going to, instead of using S for displacement, we will use X because we're moving sideways, and this makes it easier to think about. It doesn't matter, but it's just easier to keep track of. Force, every spring, if it is uniform, that's key, has an associated constant with it. You don't know what it is, you have to figure it out, you have to measure it. But the stretching and compressing don't change the constant. So if I have to use a certain amount of force to compress it a certain distance, or I use the same amount of force to stretch it the same distance, I can then figure out what my spring constant is. Okay? So the constant would be measured in force per distance, and we just leave it like that. So newtons per meter, or it could be pounds per foot, whatever units I'm using. For this, we're going to probably stick with metric just because it makes it a little more consistent. Now, the work done. Now this is where it gets a little bit trickier. Okay? I want to push a refrigerator across the room. Okay, let's say that refrigerator weighs, I don't know, 500 pounds. And so I unlock the wheels and I'm going to push it 50 feet. So how much work does it take me to push that 500-pound refrigerator 50 feet? Well, it'll just be 500 times 50 foot-pounds. Now, this is the Calc 2 problem. But in Calc 3, I want to push that refrigerator, but I'm going to go off at an angle 50 feet. So when the question is, how much work did I get done across the room? Do I get to use all 50 feet? No. I'd have to project straight across. I probably have something less than 50. In fact, there's a cosine of theta involved there, isn't it? Oh, I want to push that refrigerator, but somebody decided to tilt the room. So when I went to push it 50 feet, I went sideways 50 feet. How much work did I get done pushing across the room? 0. I'm not 1 inch closer to the other side of the room. I'm on an incline. So I unlock the wheels of the refrigerator and I go backwards 50 feet. How much work did I get done pushing it across the room? I got a negative amount of work done. Yes, work can be negative. That confuses the heck out of people. How do I know? Because I now have to do a positive amount of work just to get it back to the start. That is the real situation when it comes to work. Here's what we're going to do in our class. We're going to be pushing it in the exact same direction that our displacement is at all times. Not this. So there's no cosine of theta we have to worry about. That's next semester. That's more realistic, but for now we're going to do this because that involves vectors and dot products and things that we don't cover in this class. That's Calc 3. That's not hard. That's just where we're going to reserve that. So in our class, our force will always be in the same direction as we're trying to go. So we can just simply multiply the two together. You okay with that? Hopefully you are. So what about the work though? If I have to do something and I'm moving in a certain distance, I have to integrate to get to the work. Okay, I can't simply multiply. So if I wanted to know the work done, it's going to be, I'll just write from A to B, from my beginning and ending of what? Of the force. But why? Because X isn't a constant. I am pushing it through something. That's why I said this is probably the easiest formula anybody's ever going to use in a calculus class. It's really, really simple. So let's do a problem. This is the lowest level of work problems. So let's say a force of 100 newtons is required to stretch a spring, let's say 50 centimeters from its natural length. Let's start with that. Now, what do you think we mean by natural length? I mean that. It's just sitting at rest. It's not doing anything. So it means the spring's got to be probably longer than 50 centimeters to begin with, otherwise I can't stretch it that far. Natural length means just sitting there. Do I need to know how long the spring actually is to answer this question? Not at all. This spring could be 100 miles long, it could be 100 centimeters long. I'm just going to stretch it 50 centimeters from that point. Now, sometimes the question will be saying, the spring is this long, and now you're going to move it, this much further, so you just, subtract. So, I need to figure out my spring constant. I haven't asked the question yet. I'm just showing you how to find K. So, how do I find K? Well, that's a force. That's a displacement. I did something very tricky here, though. All right, I would like you guys, really quickly before we leave today, I want you to measure the area of this floor. So I'm going to hand you a yardstick, and I'm going to hand you a meter stick. And you guys, you go this way, and you go this way, Austin, okay?
Wait, what?
Is this going to work?
Aren't those different units?
So you come up with the room is, 347 inch centimeters. That's not going to work, is it? Why won't it work? Because they are different units of measure. You can't measure the area using two different units of measure. I just asked you an impossible question. Why? Because what are newtons? measured in?
Kg meter per.
Meters. You can't work with those.
We gotta convert just to get it.
So I either have to change newtons into something else. Anybody know what it is if I'm using centimeters?
Oh, gosh.
Dynes. You're never going to use dynes. Dynes would be really small. Or I can change centimeters to meters. Everybody got that? I can't use 50 centimeters. All my numbers will be wrong by, powers of 10. So what am I going to use here?
0.5 meters.
I'm going to use 0.5 meters. That's not a trick question. If I'm only moving something 50 centimeters, it's 50 centimeters. If I ask you how tall you are, does anyone here know how tall they are in centimeters? Would you give me a decimal amount of meters? How tall are you? Didn't say.
171 centimeters.
So would you tell anybody I'm 1.71 meters? That just sounds goofy, doesn't it? You say I'm 171 centimeters. That's easier to say. It's more convenient, it's more practical. But if we're doing this kind of problem, you'd actually have to change that into a decimal amount of meters. Not wrong, but I can't do other things because of mismatching units. So what is my constant? It's 100 newtons over 0.5 meters, which is 200 newtons per meter. There is no thing, newtons per meter isn't its own unit. In fact, that's never going to be the answer to a question. But why is that important? Because when I multiply that by the displacement, which will be measured in meters, I will get back to newtons. Okay, now I'm going to ask the question. How much work is required to, let's say, compress the spring from 20 centimeters to 80 centimeters beyond its natural length. Again, remember I said we're going to assume the spring is really long so I can move 80 centimeters. That's not an issue. Now, I didn't say from rest this time, did I? So how does this work? So here's the thing. The spring is right here. So what I'm going to do is I'm going to push the spring in 20 centimeters, and then Chase is going to come and you're going to take over from there and go from what? 20 centimeters to 80. Everybody follow that? So we're not counting the first 20. He's starting 20 centimeters in and then going 80 centimeters. Would it be any different if we took the spring and I stretched it 20 centimeters, handed it to Chase, and he stretched it another 80? No, it's the exact same value mathematically. Everybody got that? That's important. That's because of the uniformity of the spring. So whether you're compressing or stretching is irrelevant. Some textbooks will actually put a negative sign in front of that because it's very confusing. The work I do is going to be the opposite sign of the work the spring is doing. One of Newton's most important laws, and it always confuses people, for every action,
Equal and opposite.
there's an equal. By the way, those are not good words. It's for every action, there is an action of equal magnitude in the opposite direction. Anybody ever hit a punching bag?
Yeah.
Why is it when you plaster that punching bag, does it feel like the punching bag is hitting your hand back? Because it is. The same amount of energy you just deposited, which is called, the study of motion is kinesiology. That's called kinetic. And the energy that it just took in and it feels like it's putting back to is called the, starts with a P, potential. That's why they're the same. Kinetic and the potential, but they're opposite directions. It's actually not that complicated, okay? You've got the water moving through, and spinning the turbines of the dam and all this, right? The motion is called kinetic energy. What we're storing is called the potential energy. It's not that big a deal, but they're the same numerical values. But the direction, so the spring is working against me. That's why it's an opposite sign. We are not doing anything with opposite sign because I'm asking how much work you are doing. You can't do a negative amount of work if you are physically moving the spring. You're doing a positive amount of work. Everybody got that? And now, compressing, but wouldn't compressing be one sign and stretching be the other? Just make both of them in the positive direction if it helps you. So How do I answer this question? Well, what is my force? This spring has a force of what? 200x. That was my K. So what am I integrating here? 200x dx from
0.2 to 0.8.
good 0.2 to 0.8. Ah, because it was centimeters, I got to convert it. Now, this is a killer integration, right? What's the antiderivative of 200x dx?
Well, 100x.
100x squared. I'm evaluating from 0.2 to 0.8. Somebody get out the calculator. What will that give me exactly? $60 what? Not watt. W-H-A-T. Units. Joules. Beautiful. This is one of the big shames that I find, that you did all the calculus flawlessly, but believe it or not, the majority of us are going to get the units wrong. I need you to get the units right. You did the math perfectly, but it's not going to work. I taught remedial algebra for a long time, and I remember doing distance rate time problems. You know, Biff Rhodes bike, you know, this fast for this long, blah, blah, blah. And I'd say, well, you know, I'd ask for the answer, and you'd say the answer is 10. And I'd say, well, is that 10 miles? 10 miles per hour? 10 hours? Because I'm asking a distance rate time problem, and I asked you for one of the three things, your answer can't be 10. It's got to be 10 hours or 10 miles per hour, right? It's got to be something with units on it. Even in the remedial algebra, we did the math perfectly. We got the right number, but often we'd have the wrong units. So if it's like I asked you how tall you were, and you said, well, 23 years old. It's not really helpful, is it? So we want to get the units right, and because it was a metric question involving newtons, the answer is going to be joules. If it were English standard, what are the units probably? Because we're going to do a problem like that. Foot pounds or pound feet, it's the same thing. Okay, we don't squish those together. Now, if I have a foot pound per second, that is now a, what is the term? What is the, if I'm doing the work per time, that's called?
Power.
Power. Metric, the common one we use is watts. Yeah, we say common is kilowatts. No, kilowatts, that means 1,000 watts. What is the English standard? If I'm doing a foot pound per second, you'd never get this one in a million years. I'll give you a hint. It involves horses.
Horsepower?
Horsepower. It's like power. Yeah, that's what horsepower is. It's the English standard version of watts. They are equivalent. Now, is there a multiplier? For example, can I go back and forth between a newton and a pound?
Yes.
Yeah. Yeah, there's a little over 4 newtons in a pound, for example. Can you go back and forth between an inch and a centimeter? Yeah. And if you have to, you probably either have memorized the conversion or you can look it up pretty quickly. Can you go back and forth, like, between liters and gallons? Yeah. Yeah, there's a simple multiplier. You can always look it up. You don't have to memorize things like that. Now, we're going to do one a little bit more complicated. Do I have any sailors in here? Any military, any Navy guys? Okay, you've worked on a ship before?
Yeah.
You ever had to bring up the anchor?
Thankfully, no, but I know how it's done. Well, actually,
Certainly not by hand, I would hope, right?
No, hydraulics.
Anybody ever seen an anchor on a ship? They're big.
Yeah.
And so the ship's out in the dock, out in the harbor, and I don't know how deep it is. Maybe it's 50 feet deep. I don't know. I'll just throw out a number. So maybe it's 50 feet of water. So the anchor's sitting on the bottom, 50 feet. And that anchor can weigh thousands of pounds. So we want to pull the anchor up. So I have to take the weight of the anchor and multiply it by the distance that I pulled it up. You all agree? And that would tell me how much work. And that's all I'd have to do is calculate that, because everyone knows that the anchor is attached with dental floss. No, wait a minute. The anchor's attached with chain that's really huge and really, really heavy. So why can't I just multiply the weight of the anchor by the distance I pull it if I'm trying to find the work done?
Because you got to factor in the chain.
Yeah, and the more I pull up the chain,
Get lighter.
the less chain I have to pull up. Oh, so this is a calculus problem now. It's a calculus problem because the force is variable. So that's the next type of work problem we're going to look at, because this is a pretty realistic problem. All right, so here's the thing. You're on the edge of a cliff, and here you have a pulley, and attached to the pulley, let's say you have 1,000 pounds. Sorry, that's 1,000 lbs. And again, it's not attached with dental floss. I probably have a cable that has some weight to it. And let's say from here to here, I don't know, let's say it's 200 feet. Now, the cable, it's a pretty strong cable. So let's say the cable weighs 2 pounds per foot. That would actually be a pretty heavy cable, but I'm going to need something heavy. So I'm going to pull this thing up. Now, can I simply multiply the 1,000 by 200 to find the work done in pulling up just the weight itself?
No.
Yeah, because that's not changing. But I have to do something about the cable because the cable is changing. So the way we think about this is, let me erase this part. If I think of this as in short little sections, right? Think Riemann sum. I have all these short little sections. There's one little section. And let's say that thickness, well, the first thickness is called delta y1, the second one we'll call delta y2, all the way down, and this one will be delta yi. It's the ith one. Okay? This is a brand new blue one. Now, I've also got to pull this a certain distance. Now, do we want to call the bottom 0 and the top 200? Or do we want to call the top 0 and the bottom 200 as in depth? Or does it actually matter in the long run? Probably doesn't matter in the long run. Okay? So if I say that this is, let's call the bottom 0, okay? And then call the top 200. Then I am y feet off the ground here. Agreed? So how far does this have to be pulled? 200 minus the ith y. Oh. Now, this here, how heavy is that piece? Well, wouldn't it be 2 pounds per foot times delta yi feet?
Okay.
You with me so far? And how far am I pulling it? I'm pulling it this, so I'll call it the ith slice. I have to go 200 minus yi multiplied by 2 times delta y. The units for that, this was what? Force per distance. Delta y, it's distance. This was force per distance. This is distance. What are my units so far then? Or what overall thing have I found? Distance, force per distance, distance again.
Energy?
Or work. Same thing. But I'm asking how much work is done. And again, energy and work are the same thing, but it's a context thing. I'm asking for work. So we'll call this the ith piece of work. That seems like a lot, but that's not complicated. Now, going back to count 1 for a moment, the way we did these problems in count 1, we said, let's now add all of these up. I have n of these. I'm going to add all of them up, and that will give me a reasonable estimation of my overall work. So I want the sum from I going from 1 to n of this. Where the y is ranging between 0 and 200. We know now if we take the limit, as the thickness approaches 0, right, the norm of the partition approaches 0, we can write the definite integral. This is the estimation, this is not the answer, but we know how to go from the sum to the integral. Hopefully, you know, that was a big part of Calc 1. I can go directly now. And y is going to range from what to what? 0 to 200. And here's why this setup is preferable, that I'm calling this the distance. What if I said, I don't want you to pull the rock the weight all the way to the top. I just want you to pull it up 50 feet. I want you to pull it up 175 feet. I want you to pull it up less than all the way to the top. Then you'd just go from 0 to how far you pulled it up, wouldn't you? Does everybody understand that? And that doesn't make it a different setup. That makes it actually an easier problem. Now, is there anything wrong with me saying, let's call y the distance we're pulling it, and y can go from 0 to 200? No, because next day when we're going to do fluid force problems, and I'm going to talk about being out in the ocean. Okay? Any divers here? Anybody ever dive? So, do you say, I was out in the ocean and I was diving 100 feet from the bottom of the ocean?
No.
Do you say that? No, you say 100 feet from the top. You don't say I was at negative 100 feet, you say I was 100 feet deep. In other words, when you're talking about water, you measure depth this way. 0 is at the top and you measure positively going down. Isn't that correct? Nobody says, yeah, I was 6 feet from the bottom. No, I was 6 feet from the top. But we measure depth that way, with a backwards scale, in other words, and it doesn't cause any problems. So we could have done the same thing here. I like this setup a little bit better. Now, what is my final answer going to be measured in? What units?
Joule.
Feet per pound.
Pound, feet, or feet pound. Yeah. Can't use joules unless I know what the metric conversion is. Don't worry about it. You're not going to do that. So because I'm giving you English standard, you would measure your work now in pounds times feet. So pound, feet, foot, pounds, one is not better than the other. It doesn't make any difference how you say it. Does everybody understand? That's how we do this one. All right, I'm going to move on because the actual calculus of these problems is trivial. But as all applications, you know, it's never about the answer. It's always about the setup, isn't it? If I set it up correctly, it's probably easy to navigate. Think in Calc 1 for a moment. You learned how to integrate. You did a lot of integrals. Sometimes they were really complicated. You had some messy substitutions. Then you did your applications. You did things like, you know, the area bounded by the curves, or maybe you did, I don't know, the volume by rotation when you're slicing. But your integrals themselves, you were integrating, you know, x. You were integrating something utterly trivial, and it's like the easiest integrals you did. Why? Because the applications, you usually use really, really friendly things that made really simple integrals, because the problem wasn't about the answer, it was about setting it up correctly. When you think about just the straight up integrals you did, just here's a bunch of integrals, they were way more complicated integrations than your application problems were. I can guarantee you that across the board. The applications, and you can go all the way back to remedial algebra. You learn the technique, you learn the methods, and then you do the applications. The math required to do the applications is usually less than the math you just learned, because it was all about the setup. You're going to find the same thing in physics. The actual calculus you're performing probably won't be that bad. It's all about the setup. If the setup is correct, you're probably going to get the answer right, because the rest of the problem is not going to be the challenge. In the work problems, the calculus is going to be trivial. I mean, my gosh, integrating a linear function. Doesn't get much easier than that, but it's getting the right setup. So now we're going to do one of the few applications that we will repeat next semester. So this is an intro. This is an artificial problem we're going to do next. And I say artificial because we're going to do a two-dimensional problem when it's really a three-dimensional thing we're looking for. Now, at the end of this class, our goal is to have mastered the calculus of two dimensions. Calculus 3 is to master the calculus of three dimensions. So why do we got to do that? Okay, I want everybody to close one eye. Close one eye and look at me. This is all the math you've done in your entire life and through the rest of this semester. Is this the real world? No, open your other eye. What's the difference?
Depth.
You went from 2D to 3D. You have to master the math of two dimensions before you can talk about the math of 3D. And all you're going to do is take everything you learned and extend it, and I'm going to show you. You're going to like Calc 3 more than you liked 1 and 2 for many reasons. A lot of times it's because problems that were challenging become easier if you look at it from a different point of view. If you step back and look at it from a three-dimensional point of view. I'm going to show you things, you're saying, I didn't know I could do that, but boy, it makes things easier because I'm now in 3D. You live in 3D. You're not going to do physics in 2 dimensions. We can't do only math in 2 dimensions. So you master the calculus of 2 dimensions. You've mastered the mathematics of real numbers in 2 dimensions. Oh. So then Calc 3 is you've now mastered the mathematics of real numbers in 3 dimensions. And then we throw another twist at you when you start the higher levels of math. And you realize that the world isn't all real numbers. So then you have to throw in the complex realm, and all of a sudden, boy, you talk about it opening up. And you talk about, and when I'm teaching differential equations, every semester I'll have students, they'll say, you mean everything I was ever told was a lie? I'll say, no, 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 no. The truth was just withheld. You weren't lied to, you just weren't told the whole truth. You were told a partial truth. You see, once you introduce complex numbers, first of all, have you ever given a correct answer of no solution to a problem in any math class? Yeah, it's not actually a possible answer. It was always the wrong answer if you step back. There was no real solution. There was always a solution. There's no such thing as a prime polynomial. All polynomials can be factored, they just don't all have real factorizations. You know, things of that nature. Everything works. You're not going to do anything with complex numbers in the calculus realm. You'll start the process in difficuse, and then, how many are engineering bound? Maybe your first upper division class, which for a lot of you will just be maybe 3 semesters from now. You're going to do the calculus of complex numbers. It's called complex analysis. It'll be one of the first upper division classes you take. And then you see that a lot of the things you held near and dear to weren't necessarily completely true. You can do things. Okay, you guys all know all the mathematics that Chuck Norris can do, right? Everybody knows. You know, Chuck. He was a student in one of my classes years ago. You know, the counting to infinity thing. You just count by 5s. It's, you know, but you know, Chuck can divide by 0. Anybody can divide by 0 when you've had complex analysis. You realize it's actually just a parlor trick. Yeah, you actually, when you get into the complex realm, can do things that you can't do in the real realm, and it helps answer a lot of really important questions. So after you master the calculus of 2 dimensions, you then go to the calculus of 3 dimensions in the real world, and then eventually the complex realm, and there are now no unanswered questions. If you're a math person, you still embark in the complex realm because you need to know where there are restrictions. Well, I'll just leave it like that. Not everything has restrictions, but sometimes. In our class, we have restrictions, so we're only going to do real valued things. And when I say real valued calculus, the term real value means real inputs and real outputs. Can you take the square root of a negative number? Well, half of all square roots are going to be square roots of negative numbers, and yeah, you can, but they're going to be imaginary. Can you take the logarithm of a negative number? Yeah, but it's complex. So if we're talking real numbers only, no, we restrict the domain. But if we are allowing everything, no, the only thing you can't take the logarithm of is 0. Now, even Chuck can't do that. He tried, he gave up after a while. Now, you can't take the logarithm of 0, but you can take the logarithm of negative numbers, and there are very important formulas that are a result of that. Wow, and we are going to look at some of those a little bit even in this semester. So here's the idea. Okay, how many have ever taken their car to the shop and then they raise the car up in the air on, I don't know what those hydraulic jacks, you know what I'm talking about? Yeah. Okay, so here's what happened. Before class today, this row here, I have a hydraulic jack that I put under the row. So your row is going to come disassembled. And what I'm going to do is lift the hydraulic jack, and all of you guys, you're kind of on a beam. You're all going to go up in the air. What if I put the hydraulic jack under Connor's seat, though? Is that going to end well for all of you? As I start lifting, what's going to happen to all you guys, especially you in back? Oh, yeah. You're going to fall off, aren't you? Yeah, it's probably not going to work. So is there a place that I should probably put the jack? Kind of, yeah. There's got to be kind of a middle. Do you all agree that there's got to be a middle in there somewhere? And it would seem reasonable that there has to be really one exact spot that will balance the best. If you took your car to the shop and they didn't center your car on that hydraulic jack, your car's probably going to fall off. That would be bad. So I want to know where to put it. So here's really what it comes down to. Connor's a mass point. You are a solid mass, but I can literally shrink you to one point. Now what I'm going to do is make your point be on the floor, because we're doing 2-dimensional centers of mass. We're not doing 3. 3D is next semester, but we start with this. The lecture I'm giving now, I repeat next semester before we get to the 3D so everyone can segue. So I'm going to shrink you to 1 point, but you're on the floor. Now, you're going to be another point, but your points are separate. They're discrete. It's not continuous. Everybody agree? There is a separation. So I have your mass point, your mass point, your mass point, and so on. 1, 2, 3, 4, 5, 6, 7. I have 8 individual mass points, all located, and let's say you're all on the same line to make it easier. They are 8 discrete mass points. This is how we always start the process to figure out the center of mass. So I draw it from a picture standpoint. It's a dot, dot, dot. So at x1, we have m1. At x2, we have m2. At x3, we have m3, and so on. And here at the nth, I have n mass points. Now, to make it easy, I could say, let's call the wall 0. And then you are, I don't know, what, probably about 8 or 9 feet? Okay, then you could just be at 8. Or I could call you 0. It wouldn't make any difference where I start. Now, as long as I measure everything from there. So let's call the wall 0. So this is Yukon. Okay, now are all the masses equal? No. Are all the distances equal? No, they don't have to be that. They're just random. So I have this. Now, let's make a simple assumption. Let's assume there actually is a center, a perfect balance point. I don't know where it is. Let's call it right here. And for a lack of a better name, we'll call that x bar. Now, to give you a little bit of insight so you can think about this and make some sense. All right. Okay. What's this called?
Seesaw.
Or
Lever.
you're all teeter-totter. Seesaw, teeter-totter. All right, you were all kids once. Anybody here have kids? I got a lot of kids. They love teeter-totters. You know, this would be me, this would be one of my kids, and they tended to get airborne often. What's wrong with this picture? They're not going to balance, right? This teeter-totter is going to be like this all the time, isn't it? What is this called? It's called a fulcrum. How can I get this to balance? Just don't get mathematical on me. Just
Closer to the bigger person.
yeah, get closer to the big kid. If I move the fulcrum closer to the big kid, it might balance. Now, the teeter-totter itself is called somebody said, a lever. Now this goes back, this is not new math, this is thousands of years old. I actually did this once. Years ago I had a friend, their car got stuck, we were up in the Lagunas, and the car got stuck in the mud, and then the next day we went to get it and it kind of froze and it was really hard to get out. And there was like, you know, a bunch of guys, and we had a really hard time with this. But we had this big long lever, and I said, let me try something. So I got a rock, I put it over next to the car, put the lever, and then I lifted the car off the ground, and they thought, my God, yeah, they were looking for the S on my chest and, you know, my cape tucked in, like, how did you do that? And I just laughed, and like, I learned that as a child. It's exactly what he said. If you move the lever, if you move the fulcrum closer to the big kid, it might balance, because there's a calculation taking place here. This kid has, let's call it mass 1, and this kid has mass 2. This distance here we'll call x1, and this distance here we'll call x2. When will it balance? You may or may not have ever seen this before. It will balance when m1 times x1 is equal, and those are called the moments. The moment is the product of the mass and the distance. Now there's no unit. Moment is used to help us calculate other things. So you don't have like joules or watts. The moment is simply mass times distance. You will balance when the mass times the distance is exactly the same. So if this kid weighs twice as much as this kid, as long as x2 is half of x1, it will balance. So how in the world was I able to lift the car? I moved the fulcrum, the rock, really close to the car. So the distance between the fulcrum and the car was very small. The distance between me and the fulcrum was very large, proportionally. And so even though my mass was nowhere near the car's mass, I was able to move that. That's how it works. So can I use that here? Absolutely. So the moment here would be what? Not m1 times x1, but m1 times this distance, or difference. You agree? So if I said, all right, let's take m1 times x1, let's add it to I'm sorry, I said difference. Let me do that again. m1 times x bar minus x1, there we go, plus m2 times x bar minus x2 plus all the way down to mn times x bar minus xn. That would give me the total moment of this situation, or would it? Anybody know what that has to add up to? It's not a trick question. Aren't roughly half the masses on one side of the fulcrum and roughly half the masses on the other? And let's say this is in the perfect spot. This is exactly where it needs to be. Then all the things on the left will add up to a certain positive amount. But what will all the things on the right add up to?
Exact but negative.
Exact but negative. Because now this quantity would always be negative. So therefore, what does this have to add up to?
0.
0. And that's how we solve the problem. Not because I told you, but if that x bar is exactly where it's supposed to be, then the moment on the left has to equal the moment on the right. But I don't know the value of x bar, so by adding them all up, I'm expecting half those values to basically be negative and cancel. If I knew exactly where x bar was, I'd say equals the other side, and I'd reverse the order of subtraction. Well, to set this up then, let's distribute. This is going to generate our calculus formula in just a moment, by the way. No pun intended. So I have m1 x bar minus m1 x1 plus m2 x bar minus m2 x2, and we'll go all the way to the end. Let's assume n is large. Okay, now let's gather things. First of all, let's get all the x bar terms together. And I'd have m1 plus m2 plus mn all times x bar. And let's take all the minuses and throw them on the other side. Then that would equal m1 x1 plus m2 x2 all the way down to mn xn. You with me on that?
Okay.
If I add up all the mass points, if I add up all of your masses, doesn't that just give me the total mass? This gives me the total mass of my system here. So let's just call this M for mass, total mass. Wait a minute, M1, X1, these are all pluses. Won't that be the total moment? Now, I wasn't there when the Universal Math Council got together and decided to put variables on things. I probably wouldn't have used, S for arc length and M for slope. Does anybody know what symbol we use for moment? M.
Oh.
And moment is only used in conjunction with mass. Yeah. So what do? We use a little m for mass and a capital M for moment. Just make sure you make your capital really obvious capital. It was a terrible choice. Now, I'm actually going to give it a subscript. And the reason is we're going to do things in 2 dimensions and we're going to do things in 3 dimensions. Next semester, I have a point in space. It's right here. Don't I have a distance to the floor and a distance to that wall and a distance to that wall that I have to take into account? That means I'd have 3 different moments. In 2 dimensions, you're going to have 2 different moments. The distance to the y-axis and the distance to the x-axis. Right now, this seems like a 1-dimensional problem. It is. So I'm measuring all my distances where? To the y-axis. I'm not really truly in 2 dimensions yet. I'm 1-dimensional, but all my distances are measured to the y-axis. So that's why we call it a y subscript. Okay? X bar is simply the total moment divided by the total mass. It's actually that easy. And when we go into the calculus, it's going to be the same thing. It's actually going to be pretty simple. Isn't that cool? That's not a complicated formula. Now think of units. What are the units of moment? It was mass times distance. I'm dividing it by mass, and therefore my answer is in terms of distance. X bar is the distance to the y-axis. So that's consistent from that standpoint. So units aren't really a thing here I have to worry about. See, center of mass is a location, it's an address. It doesn't have units. It's just a place. Now, in 3D, okay, and again, we will spend a lot of time on this in Calc 3. These desks are a perfect example. I love using these desks. See the desk? Everybody see the desk that's holding the door open? Those are the evil old desks we used to use. How many have ever sat in one of those?
Yeah.
Why are they evil? Well, besides the fact that they hate left-handed people, but that's another thing.
Friggin' tiny workspace, tiny.
Everybody put your backpack on the end of one before you sat down? What happens?
all over.
Tips over. Anybody ever seen anybody sitting and lunging forward for their coffee or something? They tip over. I've seen many accidents in them. They are a lawsuit waiting to happen. They tip over because they were poorly made. It's a three-dimensional object that we have to consider center of mass. Now, I'm going to give you a really simple example. I would like the center of mass of this desk. Well, this desk is only made of 3 different materials. So like I said before, can I take the desk top and shrink it down to 1 point in space? With equal mass, by the way. Take the seat, do the same thing. Take the metal bar, do the same thing. I'd have 3 separate mass points because there's only 3 different materials. Could I find the center of mass using those 3 points? Yeah, we can't do that this semester because it's 3-dimensional, but it's actually not that complicated. Where do you suppose the center of mass of your desk is roughly?
Where my knees are.
Yeah, that's probably a good example. It's definitely down low, isn't it? It's probably where your knees are. I don't want you to try too hard, but I do this in Calc 3. I'll say, I would like you to, while you're sitting there, tip your desk over, and it's actually pretty comical. I'm only going to give you a half hour. You can't. Not if you're sitting down. It's not possible for any of you to tip your desk over, which is why they're so good. They're so safe. So why did we use those things there for the first 50 years of Mesa's existence? Because our classrooms were a lot smaller. And we had to have 48 seats in every class. The class limits were 46, but we had to have 48 chairs. There's supposed to be 54 chairs in here. These classes are significantly bigger. So why did we have those? Because do you know there's actually a law that says how far apart you have to be? Did you know that? There's actually a law. It's been around since 1991. It's called the Americans with Disabilities Act. You may know how wide these have to be?
Wheelchair width.
Wide enough to get a wheelchair through. That's every single row in every classroom in the United States. That's an actual federal law that we were violating for many, many years because we had too many classes. We had an instructor who was in a wheelchair most of his life. And he'd get into classes and the students would have to move things out of the way so he could simply get to the front of the room because we had too many students, too many desks. These desks are awesome, but we couldn't have these back in those because we couldn't fit more than about 30 of these. But these are great desks because they were engineered correctly. Now, we are going to talk about the engineering in 3D, right? Things like automobiles. We're talking about human beings. We're going to go into tremendous detail because if you're an engineer, it turns out that's one of the more important things is to understand the concept of center of mass because it has everything to do with product designs of things. Anybody here ever worked at a grocery store? Did you ever do the end caps? You know what those are? At the end of every aisle, they always have things displayed at a grocery store. And things are usually stacked. Anybody ever seen them wipe out or fall down? Or yeah. Apparently there's a story being told, I don't know how true it is because my mother tells the story where, I don't know, maybe I was 4, I'm in the shopping cart, we're at a grocery store, and the end cap, they had stacked all these bottles of expensive alcohol, And as we're going around the corner, I reached out, and the entire thing came crashing down, and it was like, a lot of money. And they tried to, make us pay for it, and I still think to this day, I'm 4 years old. If I could reach out with one finger and pull the entire display down, it wasn't a very good display. They didn't take into account that you don't stack bottles vertically, 10 feet in the air in such a way that anybody here ever move, you got a moving truck and you loaded it yourself? Anybody ever do that?
Yeah.
This is why you hire people. Because when you got to the other end, all your stuff was everywhere, wasn't it? It fell everywhere because you didn't take into account things like center of mass. In other words, it's something as simple as that. If you don't take into account, it can end badly. So we spend a lot of time in Calc 3. I have been told by former students who are engineers now, they said that's the one thing they use more than anything else. Because it's so everyday life when you're designing something. Again, think of an automobile. Think of a building. Of course, we make buildings that go like this, right? They get wider as they go up. Do we do that? Or do we maybe go the other way? Why do we make buildings that get narrower as they go up typically?
Counterbalance for all the pressure that's going downwards.
Or keep it real simple, where do we want the center of mass of the building to be? Closer to the ground than the top? We do live in California. Why would that be relevant?
Earthquakes.
Earthquakes, yeah. In other words, it's sort of a common sense thing, but that's why. Yeah, we would rather have the center of mass be lower than higher. So the concept of center of mass, now how do we change this into a 3D problem? Well, we don't in this class. This class is artificial. I already said that. We are not doing three-dimensional centers of mass because we can only do the calculus of one independent variable for now. When you did volume problems in Calc 1, volumes by rotation, think about that for a moment. Why volume by rotation? Because your cross-sections were circular in nature. If you think about all the application problems you did geometrically in Calc 1, in 2 dimensions you only used circles and squares, and in 3 dimensions you only used spheres and cubes. Why is that true?
Because it's all constant. You can use pi.
Well, it's how many variables?
One.
1. You didn't do just simple rectangles. Oh, because that would require more than one independent variable. In Calc 1 and 2, we can only do the calculus of one independent variable. So we're really limited with the geometry. And then we get to Calc 3, we remove all those restrictions because we learn how to do the in-betweens. So here's what we're going to look at. We have something. I have a 2-dimensional object. It is bounded here by y equal f of x, here by y equal g of x. We'll keep it simple, going from A to B. Now, if I asked you to find the area of this thing, this would be simple. This is what you spent a lot of time, hopefully, in Calc 1 on. So I'd take an arbitrary slice, if you remember doing this, and I'd say, okay, let me find the area of that ith slice. And the area of the ith slice would be f of xi minus g of xi multiplied by its thickness, which would be delta xi. Look familiar? And then you say if I add all of them up and I take the Riemann sum, I had another blue pen here. Well, then we'd usually just segue right to the integral, didn't we? Because once we understood the Riemann sum was take the limit of the summation, now I write the integral. The integral is going to look like this. I know my area is simply going to be, I know this. I have no doubts. That's what we did in Calc 1, and that is absolutely true. So how do I find the mass of this thing? Well, now what we're going to do is we're going to assume that I have a shape. Okay, look at your desktop for a moment. You guys can't see this clearly, but if you look at the top of this, what you see are strips. You see long strips. Okay, anybody know what I'm talking about? Anybody have like a hardwood floor at home? Anybody know what I'm talking about? You have strips of wood. We will make the assumption that a strip of wood is uniform. It's exactly the same density, but the next strip of wood is completely different. In fact, it doesn't even have to be the same material. My desktop, if you look at this, you see a bunch of really thin strips. You see many, many, many of them. The assumption we will make is really simple. This strip is of uniform density. The mass will not change anywhere on this strip. Where will the mass change?
The next strip.
The next strip, exactly. Each strip is independent, but within a strip, it's going to be the same from top to bottom. The reason I can only have one independent variable. And so therefore, this thing here will have density, and we'll use a Greek delta. Now, the units for density, this is a confusing thing in general. When you get into 3D and you realize, oh my gosh, I can talk about one-dimensional density. We did that a moment ago, right on a number line. I can talk about two-dimensional density. Now we're in 3D, right? Think of the human body. But density, there's actually 2 versions of density. See, density can be mass per unit length, unit area, unit volume, or it can be weight per unit length, unit density, unit area to unit volume. And by the way, they're all correct. It depends. What are you using it for? Where have you, anybody here fill up their tires recently? Anybody ever fill up their tires? What do you measure? What are the units you're measuring when you fill up your tires? What is that?
Pressure and force.
Pounds per square inch. Is that a density? Yeah, it's weight per area. It's a form of density. Now, anybody here ever, I asked you that earlier and you all said no. Nobody here ever dove? I dove in college. Is scuba diving? Okay, so when you measure density there, you're not measuring it in area, are you?
No.
You're measuring volume. That's kind of important because you're not two-dimensional. So PSIs, think of it as sort of like measuring on the surface as opposed to the whole object. Density, it's not right or wrong, it's what is the situation dictating. Our density here is going to be mass per area. That's our density we're doing here. By the way, if we change it to weight per area, it wouldn't make any difference in the calculation. But we're going to do our density as mass per unit area. Okay? Now, if I take mass per unit area and I multiply it by area, won't I get mass? So, how do I find this? Well, this is actually one of the simpler segues. The total mass would then be, well, let me go back to the ith area. I want to know, I know what the area of the strip is. It's right here. Well, what's the mass of this strip? I'll call it the ith mass. Won't it be the density times the area? So we just said density is in mass per unit area. I'm going to multiply it by the area of the strip. This would tell me exactly the mass of the strip. In other words, it really depends. It depends on that x. Because as I'm moving left to right, it's changing. It's not changing up and down. That's the artificial part. Next semester, we can add to that. But right now, it's only changing left to right because I can only have one independent variable. So if the way I get mass is to multiply by this, then how do I get the mass in terms of an integral? That's a piece of cake. I just take the density and I multiply it by this. Now, what you're going to find in a typical calculus class is your boundaries are usually going to be very, very simple. You're going to be bounded by lines and parabolas and things like that. You're not going to be bounded by exponential or logarithmic or trigonometric functions because the calculus of the integration might be beyond us at that point. There's too much going on. So we typically will bound things with really simple regions because we're trying to get the big picture. We can always, get killed with complication. But if you can't answer the question, what's the point of the question? Now, it wouldn't matter how complicated I made the boundaries. You could all state this, couldn't you? Now, in reality, if I can state the integral and I have the correct integral, in real life, I can use technology to help me navigate through the problem if I really couldn't do it by myself. But in a class like this, we really like to finish the problem. So we generally use simple things. Now, that's the mass. How do I get the moment? Because remember, I'm not just looking for an x bar now. I'm also looking for a y bar, aren't I? I'm looking for a point. So on my tabletop, I'm looking for a point that serves as the center of mass. Assuming the density is different. Well, isn't moment simply mass times distance? So if that's the ith, I want the ith to the y-axis. Don't worry about x yet. Well, shouldn't that be this? Shouldn't it just be that then? Isn't that what moment is? Mass times distance? So if I start with my area, my mass I just multiplied by my area by its density, and now my moment I just multiplied that by its distance. So can you tell me the integral for my? I think you can. I said this would be fairly simple. So far so good? Because again, if I add up all these and I take the limit of the sum, I'm going to get this integral. So this seems pretty simple. This seems pretty simple. Where do you think it's going to get tricky? That's x. This is how I'm finding x bar. And by the way, what is x bar? but it's this moment divided by the mass. I've got them both. I need a y bar. The distance to the x-axis, to the y-axis is the x-coordinate. That's why we call it my, because it's the distance I'm measuring. But don't I have to also measure this way? Everybody see that? I need also a distance. I said I have a point in space. I said there are 3 distances I have to measure. So we don't call it my and mx. We actually call it the moment to the xy plane, the moment to the xz plane, the moment to the yz plane. So we use different subscripts because it's the distance to that particular plane. Here's the distance to that axis. But do you all see a problem here? Those 2 are pretty clear, pretty clean. How do I measure this distance? I mean, that was easy. My strips are moving left to right. But what distance should I measure this way? I kind of gave you a hint earlier. I'm trying to find your center of mass change. Let's assume that you are of uniform density. Okay, you are made of water. You are water and skin and nothing else. Okay, so could I shrink you to a one mass point, and that point be at the center of your mass? By the way, when we say center of mass, there are a whole bunch of terms that also are the same thing. We sometimes say center of gravity, center of balance. An ancient archaic term, and you find in old books, would be the barycenter, B-A-R-I. It's the same thing. And mathematically, it's actually called the centroid. Those terms all mean the exact same thing. So when you hear one, it doesn't matter which one you hear. You're saying, okay, I'm looking for really that balance point in a sense. Okay? If I can shrink you to one mass point, can I take this strip and shrink it to one point? Didn't we say the density was uniform from top to bottom? Now, do you remember when we did the problem where you were pulling up the weight? And we said we had to consider the mass of the cable. Let me throw a thought at you. What if I took that entire cable and I put all of its mass right at the midpoint? And then I just moved that half the distance. It turns out you would have gotten the same answer. If we're picking up the anchor, if we just said, let's take all of the chain and put all of its weight right in the middle of the chain and then just move that, it would be the same answer. Why? Because of the uniformity of the shape. The chain didn't change from top to bottom. That's key. This is not changing from top to bottom. It's staying exactly the same. So theoretically, could I make all of this just be at the center? It wouldn't change this one at all, but what would it make this distance? I'm looking for a word. So you got 80 on the first test, you got 90 on the second. What's the midpoint called?
Median.
The average.
Average.
How do you take an average of 2 things?
Add them together and divide.
Yeah, you just take half their sum. It's like, you mean if I simply take half of f plus g, I could use that as my y distance? Yes. Why? WHY? Because x is the only independent variable. Next semester, x and y are going to be independent. X, y, and z are going to be independent. It actually is an easier problem, not a harder problem. I'm going to give you a simple analogy. Baby algebra, remedial algebra, 9th grade algebra, whatever you want to call it. You remember this problem? Okay, at the theater, they sell child tickets for $8 and adult tickets for $12. And last night, we sold 375 tickets and we made $4,613. How many of each did we sell? Do you remember that problem? It was called a mixture problem. So you say, okay, let X be the number of adult tickets and let 375 minus X be the number of child tickets, and you set it all up, and you could do it. It was kind of complicated. Then you took algebra 2, intermediate algebra, and you said, let's call X the number of adult tickets and Y the number of child tickets, and then X plus Y adds up, and then, do you remember that problem? That problem was so much easier. It was so much easier to conceptualize and set up. Because in remedial algebra, you only learn how to solve equations that involved one variable. But then in intermediate, you learn how to solve 2 variable problems, which eventually led to solving 3 variable problems. And then you learn how to use a matrix and all these things. But when you went from 1 variable to 2 variables, yes, there was actually an additional step of algebra, but it was so much easier to set up, and it was so much easier to understand. And if left to your own devices, none of you would probably do it as a 1 variable problem. You'd probably do it, let X and Y be my variables. When I introduce more variables, it doesn't make it more complicated. It usually makes it a lot simpler because formulas are easier, not harder. So what I have to do here is, this distance is no longer xi, but it's going to be half of this. This is what's going to go here. So what does that make my mx integral? This looks kind of complicated, but it's still going to be this, and it's still going to be this. But what's going to go in the middle now is the equivalent. I can't put a y here. I cannot put the variable y here because that means I have two variables in my single integral. And you can only have two variables in the single integral if they're both independent, which we haven't learned how to do. And then your answer, by the way, wouldn't be a number, it'd be a function, and all hell breaks loose. Dogs sleeping with cats, I mean the whole nine yards. It just, it won't work. Trust me, it just won't. So as ugly as this looks, now remember what I said about the functions you're going to be using in general? They're probably going to be pretty simple. They're just not going to be complicated functions. I mean, I tend to like to use things like lines. You know, my density, if you look at your first quiz, your density is probably something like 2x. You know, something kind of simple. Everybody here could set up every problem correctly. No matter how complicated I made the problem, you could all set them up easily. And that's actually where the value is. I would like you to be able to finish the problem. Therefore, we're making the boundaries really, really, really simple functions. Okay? You all with me on that? So this, I usually use literally lines and things like that to ask the question. I don't want it to be terribly complicated. But this is the tricky part. Because I cannot have a y here, I can't have an x and y in the same integral at the same time. Not if I only have one independent variable. Now, the answer to the question. X bar comma y bar. Now, I don't want to say this is common sense. I have a closed region here that's bounded by functions. It's not a circle, it's not a figure eight, it's not something that's complicated. I'm bounded by functions. And it's not weird. So you did the whole problem perfectly and your answer was here. What do you think of that?
That doesn't make any sense.
Good. It is bad. Why is it bad?
Because it's not in the bounded region.
It probably should be in the bounded region. Do you agree? It would make sense that it's in the bounded region because of the nature of my region. So one of the things I tell everybody to do, always draw the picture. Does it have to be in the region? By the way, can a mass be negative? No. Can a moment be negative? I'm on the XY plane. Can a moment be negative? What if your region is in the second quadrant, third quadrant, or fourth quadrant?
Yeah.
Doesn't one of your coordinates have to be negative then? And if mass has to be positive, moment can be negative if I'm in a different quadrant. If I'm in the third quadrant, then both moments have to be negative, don't they? Does that make sense? So I always tell people, draw a picture first to make sure. Now, I'm going to do a really simple example of center of mass. It's supposed to be a horseshoe. Now, you have a fairly stiff piece of cardboard, and you're going to lay your horseshoe down on the cardboard. Now, you want to put your finger in the perfect spot to balance this. Tell me, is your center of mass going to be within the horseshoe? Or would you say it's probably going to be, I don't know, maybe around here somewhere? Everybody know what a hula hoop is? Where's the center of mass of a hula hoop? Hula hoop's a perfect circle, isn't it? So where's the center of mass of a hula hoop? In the center of that circle, which is in the air, is it part of the hula hoop? No. Does the center of mass have to physically be within the region? The answer is not necessarily. Here it's kind of clear would have to be. Could you draw a region, that's the hint, where the center of mass, yeah. I'm bounded by these parabolas. So here's my region. Is it possible my center of mass is not physically within the region and I'm bounded by functions? Yes, this is why you'd want to draw the picture first, because I think we all agree that center of mass ought to be within the shape. I think that's reasonable. Does the center of mass always have to physically be within a closed object? The answer is actually not necessary. I will spend a significant amount of time on this one when we do this next semester. But this is one of the most important parts, and one of the things I've watched since I was a child. Okay, this is 2024. Last Winter Olympics were 2 years ago. Anybody ever watch the Winter Olympics? Does anybody know what the most popular Winter Olympic sport is? Significant, it's not even a close second. Women's
Ice skating.
figure skating. It's not even close. That's always been, and this was before Tanya and Nancy. You guys got to go look up. They were very famous individuals, but it was women's figure skating. And I got to tell you, I watch, but for all the reasons that my wife hates. Do you know who Evel Knievel is?
Yeah.
He was the famous daredevil. He was a motorcycle daredevil. He would jump over cars. And you can go look up Evel Knievel. He made bazillions of dollars doing this, but people didn't watch Evel Knievel for his cool, successful jumps. What did they watch him for? His crashes, his spectacular wipeouts where he would break every bone in his body and come back a year later. They watched him for the wipeouts. I watch figure skating for the wipeouts. And I can tell you absolutely with perfection when they're going to wipe out. When they jump, I'll go, they're going to beat it. My wife hates it. I do it. I watch it for the wipeouts. It's actually very, very easy to predict. It has everything to do with center of mass and centroid. I'm going to give you a glimpse because this is one of the things that 30 years ago people didn't talk about this. Now this is part of all sports research, and you've seen the people hooked up with all the different nodes and they studying them on the computer. It has everything to do with human motion. Okay, right now, where's the centroid in my body? Anybody know? I'm of normal stature. Does anybody know? Here's my navel right here. For most people, it's a little bit below the navel, kind of in the center of my body. You can tell now. This is an absolute law of kinesiology and physics. The moment your centroid is outside of your body, you lose your balance. It's impossible to maintain balance if your centroid is outside your body. It's that simple. Anybody surf? Nobody surf? Come on, you guys. Anybody skateboard? Okay, do you ever fall?
Yeah.
You think of surfing, it's an easier one. When do people surf? When they lose their balance. When they lose their balance. When they get all crooked. When does the figure skater wipe out? When they're jumping and you see them all crooked or contorted, they're going to wipe out. When you see them perfect, they don't wipe out. When your centroid physically is outside your body, which will happen when you lean forward, I'm showing you a simple example. When I lean forward far enough, it was outside of my body. It's impossible to maintain my balance. So if anybody ever watches athletes, and you're sometimes absolutely amazed that how is it that they didn't fall over? It's because they have tremendous balance. But how do they have tremendous balance? Because they maintained that one particular thing. It's kind of cool. And a little history. Okay? I told you guys I studied and trained and taught martial arts for many, many, many years. Okay, Japanese form. Who are the most revered athletes in Japan? And there isn't a close second. Samurai aren't athletes, but Sumotori. Why? Because they have the greatest spirit. Hara. H-A-R-A. Now, hara also means stomach. So at my house, when we eat a big meal, Michihara, Michihara. Michihara means big stomach. It also means great spirit. The Sumotori have the greatest spirit. That's why they're the most revered. Where was the belief that the hara resided? About 6 inches below the navel. So for many, many centuries, let's use the samurai, you wanted to maintain the honor of your family. You were defeated in battle. They didn't kill you. They allowed you to ritually remove your hara. That is called harakiri. In World War II, a lot of the Japanese pilots performed versions of that. They did it with the airplanes. One way. Enough gas to go one way only. So that act, the overall act of ritual suicide is called seppuku. Harakiri is the removal. You always have all seen Last Samurai and some of those. I mean, I'm not going to get in, but they took the blade and they cut themselves and they removed the spirit. And that was they released the spirit. That was the entire point of it. That's why the Sumotori are so revered, because they have the greatest hara. But they also have known for centuries exactly where the centroid in the human body is for somebody of normal stature. Now, what if you have ridiculously long legs or ridiculously short legs for your body type? Well, then your center of gravity is going to be somewhere else, isn't it? Would that potentially make it harder to maintain your balance, do you think?
Yeah.
Depending on, yeah. So I'm always amazed when I watch like NBA players and stuff. How did they, how in the world can these guys, 7 feet tall, do what they do? Anyway, we spend a lot of time, unfortunately, we can't do any of that mathematics this semester because we don't have all these independent variables to work with. So I'm going to do the roll thing really quickly. If you have a name that you go by other than the one that I copied off the class roster, this would be the time to tell me. All right, Zara, wave at me. By the way, I really do want to learn your names, and it will take me most of the semester. Austin and Husna. Did I say that right? Oh, okay. I can't guarantee I'm going to get it right next day, but I'll. Connor and Ryan Burke here, Ryan, and Nixon, and Vicente, and Sophia, and Gustavo, and Noah, and Garrett, and Furman, and Nicholas, I saw you already, and Oliver, and Kitty over here, and Tatum. There we go. Bella, I saw you somewhere. There's Bella back there. And Danya, and Tao One. Just Tao, make it easier on me. Okay. All right, and Tina Harrell. Did I get that right? Okay. And Justin. My eyes are kind of. And Nathaniel Jensen. Nathaniel and Shane Jun.
Yes, I go by Jin.
Just J-U-N?
J-I-N.
Did I spell it wrong?
J-I-N, Jin. I
Is
just
your-
go by it. It's just.
Is it spelled J-U-N or J-I-N?
It's spelled J-U-N. But
Oh,
go
okay,
by
I did
that.
copy it down right. Okay, so make sure I didn't mess up. And Chase is here. Oh, Chase, did you stop the recording? Oh,